Welcome to another episode of Solving Chemistry Practice Problems, where I hope to show you that you don't really need to memorize a lot of things. Rather, you can solve most of these problems by relying on understanding a few fundamentals. As usual, these problems do not cover the same topic. This was done on purpose to make it similar to what you would encounter in an exam or a test. So let's get started. The first question asks us to rank the following phenols in order of increasing acidity. And the way that I would approach such problem is that I would not start by looking at the structures. Rather, I'm going to write down what I know about acidity and strength. So if I think of an acid, and I know acids donate protons, and that gives us a conjugate base. If an acid is strong, that means that this equilibrium lies mostly to the right. And if that's going to be true, that means that its conjugate base has to be stable or happy. So strong acid means a happy conjugate base. And by happy, I really mean stable. And the rationale is that, well, if this acid knows that its conjugate base is going to be happy on its own, then it doesn't have any problem dissociating, so it's going to donate its proton. But if it knows that the conjugate base is not really happy or stable on its own, then it doesn't really want to dissociate because it's happier in this form. So for these kind of questions, then, you should really look at the conjugate base and not the acid. So let's look at the first one. And this would be the conjugate. Let's just draw it the same way so we don't get confused. Base. Now, if I look at this, is there any way that this guy is going to be stable? So through resonance, I can stabilize this negative charge. So I can draw a resonance structure like this. Where the negative charge is now on this carbon. And I can continue this. So for example, another resonance. Where the negative charge is now here. And lastly, another resonance. So this is how this conjugate base is going to be stabilized like that. So that should be fairly good for this conjugate base. Now let's look at the second one. So on the second one, we have a fluorine. Here. So I can still draw all these resonance structures same as above. So that's stabilized, but what's special about fluorine? What do we know about fluorine? So fluorine, remember, is an electron withdrawing group. So it's actually going to stabilize that negative charge even further by pulling the negative charge towards itself. So this is going to stabilize the negative charge. So right there, I know that this this conjugate base is more stable than the first one, which means that the acid is going to be stronger. Now let's look at the third one where we have a methoxy. So this is the conjugate base. And that's the methoxy. Now I can certainly draw the same resonance structures that I drew, but then again, what's special about methoxy? Especially in this position, which is para. So remember that the oxygen has lone pairs of electrons, so it can actually donate those electrons to the ring. And this can go here and here. So one resonance structure that we could draw is something, no double bond here, sorry, a negative charge. Now I have two negative charges right beside each other. Do you think that's normal? Do you think that's happy? Do you think that's stable? No, right? Those two negative charges do not like to be near each other, so this is not stable. That means that this conjugate base is not really happy. So this should be a weak acid compared to the previous two ones. And lastly, we have the one with cyanide. So let's talk about that one. Let's draw the conjugate base. Now, what do you know about cyanide? So cyanide is actually electron withdrawing through resonance. So I can draw another resonance structure. Like this. So this not only has a resonance structure within the ring, but this also also stabilizes that negative charge through this cyanide. So this is even more stable compared to, for example, the phenol or the one with fluorine that we looked at, because it has one extra resonance structure through that cyanide, which means that this conjugate base is very stable and happy on its own, which means that this should be the strongest acid. Okay, so if we were to then answer the question, this would be the strongest acid. So 1. And then we know that the third one was the weakest acid because of electron donating. And then fluorine, because it's electron withdrawing, it stabilizes the conjugate base a little bit more. So that would be number 2. And then this is number 3. Okay, and I'm just gonna throw something out for you to think about. What if we had something like this, and this? So the position of methoxy is now different. It's not in para position, it's in ortho and meta position. So then how would you rank the acid? So this is something to think about. You can comment below and let me know what you think. Okay, so let's move on to the next question. In this question, we're asked to identify the product. So for this question, the first thing that you should do is to identify any special functional groups in your substrate. So here I can see I have a double bond. And then look at the reagents and the solvents. So yeah, bromine and water. So what do I know about double bonds? I know they're electron rich, meaning that this could be my nucleophile. And I know that bromine could be an electrophile. So this is my electrophile. And make sure that you're looking at your solvent. So here we have water. Okay, organic chemistry, always nucleophile attacks the electrophile. So there. And what's special about bromine, you remember that this is where you get the bridge. So this could also attack. And we get bromonium ion. Okay. So the next tip in organic chemistry, always look for generation of stereocenters. And if I look here, I have generated 2 stereocenter here, meaning that this could actually be drawn either like this, or this. Again, some question to think about. What's the relationship between these 2 molecules? So again, comment below if you know the relationship between these 2 molecules. Okay, so I know that I have bromide ion floating around, but I also have water floating around, and this is the solvent, so it's actually going to and this is actually going to be my nucleophile and not the bromide ion. And I have 2 options that I need to think about, is that if this is going to attack this carbon or this carbon. So if I attack to the top carbon, that means I'm going to break this bond, and for a few seconds in the reaction there's going to be generation of partial positive charge. If it attacks the bottom one, it's going to be this carbon that has partial positive charge. Now, which one is more stable? So the top one, right? Because the top one is kind of, you can think of it as a secondary carbocation, whereas the bottom one is a primary carbocation. So it's going to attack the top one. I'm just gonna delete this. Okay. And so now we know which carbon it's going to attack. The next thing that I need to figure out is that what kind of a reaction does this remind you of? This attacking and then this leaving. So this should remind you of an SN2 type reaction, which means that we know that for SN2 there's going to be an inversion of stereocenter. So this becomes like this and this. And then we can draw the other stereoisomer. Okay, so see how we did inversion of stereocenter, methyl group pointing out of the picture, out of the paper. Now the methyl group is coming towards us. And last step, every time you see an OH2 plus, it's not really stable, so it can either deprotonate or leave as the leaving group. In this case, it's just going to get deprotonated. So that would be our last step, OH, Br, H, and then same thing here. So just so you know, a base is just going to grab off that hydrogen. So again, I hope you enjoyed this, and I hope that you can see that by just relying on a few fundamentals, for example, identifying nucleophiles, electrophiles, and knowing stability of carbocations, you can pretty much approach these chemistry questions without really the need to memorize anything. I hope you enjoyed it. Thanks for watching.